Problem number 22. A vertical pole has two massless strings, both of length L, attached at distance L apart. The other ends of the strings are attached to a mass big M. The mass is rotated around the pole with an angular speed omega. Which of the following graphs best gives the ratio of the tension in the bottom strings to the tension in the top string as a function of omega? Solution for problem number 22. This problem could be solved even without calculations, because if we have a slow motion for small omega, the tension in the lower string is 0, and appear for some kind of omega when we increase it. But when we increase it very much, the gravity will not affect rotation, and the ratio must go to 1. So for both conditions only C is the correct answer, because here we have 0 tension for small omega and the ratio going to 1 for big omega. That's the solution for problem number 22. Problem number 23. A rectangular slab sits on a frictionless surface. A sphere sits on the slab. There is sufficient friction between the sphere and the slab such that the sphere will not slip relative to the slab. A force to the right is applied to the slab, with both the slab and the sphere initially at rest. The sphere will then. Solution for problem number 23. When we start to pull this bottom slab, the force of friction between the slab and sphere will be in the direction right for the sphere and in the direction left to the slab. It means that the center of mass of the sphere starts to accelerate to the right, but this force of friction will accelerate rotation counterclockwise around the center of the sphere. So it means that the correct solution is D. Begins spinning counterclockwise while its center of mass accelerates to the right. That was a solution for problem number 23. Problem number 24. A particle moves in the xy plane with the potential energy U equal 9kx squared plus 16k y squared. A particle can perform several different types of periodic motion. The ratio between the maximum and the minimum possible periods is next one. Solution for problem number 24. The particle performs a simple harmonic oscillation in both x and y directions independently due to behavior of this potential. If oscillation in y direction has period t, then a period in x direction is 4t over 3. The minimum possible period is t, while the maximum possible period is the lowest common multiplier of t and 4t over 3, which is 4t. Then the desired ratio is 4, which is answer D, and that was solution for problem number 24. Problem number 25. A car is turning left along a circular track of radius r at a constant speed v. A cylindrical beaker is placed vertically inside the car. The beaker has a small hole on its right side. If the water's highest point in the beaker is height h above the hole, at what instantaneous speed does the water escape the hole from a passenger's perspective? Solution for problem number 25. The car has a centripetal acceleration v square over r. So in the accelerated reference frame inside the car, the effective gravity points down and to the right, with the additional components to the right caused by centrifugal effective gravity, G effective equal this expression. This vector points down and to the right at the angle theta to the vertical, where tangent theta equal v square over gr. Thus the normal of the water surface is also at an angle theta to the vertical, and thus the highest point on the water surface occurs at the right edge of the beaker. So the effective height of the water surface above the hole is h0 equal h multiplied by cosine theta. Here we have cosine theta equal this expression, and G effective equal this expression. Then the gauge water pressure at the hole is equal to rho G effective H0 equal rho GH. And from Bernoulli equation we can find what is the speed of this water. So we have rho GH equal 1/2 rho v square, and from here we can find what is speed v. That will be square root from 2gh, which is answer A, and that was the solution for problem number 25.